Hello there. Welcome to Data Communication and Networks weeks 6 and 7. Today we will be talking about two things, transmission media, and then we're going to be moving on towards the link layer. Transmission media is part of the physical layer. So let us begin. So when it comes to transmission media, we have two main parts. We have the guided and we have the unguided transmission media. Now, when it comes to guided media, we have some cables mainly. We have UTP, STP, coaxial, we have fiber optic along with all of them, right? For unguided media, we have Wi-Fi, Bluetooth, uh, we have radio waves, and we have infrared. So let's talk about them. So the first main thing we should learn is what is the difference between guided media and unguided? Well, guided media is where you can use physical cables and you know exactly which devices are connected to the network, right? Because without knowing, how can you connect, right? Obviously, are the devices are connected to a network or not. And then you finally have unguided media, where you can't guide it. It is not specifically known. So essentially, the problem with unguided media is that you don't know how many devices are going to connect at any given time. You can't predict the at this moment this many devices will be connected to the system. Whereas guided, you can specifically predict and you can specifically know how many devices and you can act accordingly. Okay, so let's talk about guided media. So the MVP when it comes to most guided media is copper. Why copper, you ask? Well, it is cheap, it is easy to install, and it is highly conductive. Since most of the guided media uses electrical signals as its signals, copper is a really good wire or cable type that can be used in all of them. So let's talk about UTP, which uses copper, STP, which also uses copper, and coaxial. So when it comes to UTP, STP, coaxial, let's talk about what UTP means. UTP means unshielded twisted pair, and STP means shielded twisted pair. We'll talk about coaxial a bit later. So first off, why twisted pair? Why do we need to twist wires? Pardon me for my ugly drawing, but I would like you to think, why do we need to twist these wires like this? Well, it is to cancel out their noise, to cancel out the EMI that is caused, the electromagnetic interference that is caused by each of them, right? So it is to, the exam friendly answer will be to cancel out the noise, right? So that is why we twist wires together. Uh, Essentially what will it will do is, since one is a negative and one is a positive, usually most of the time, what they will do is their magnetic fields will cancel each other out. So if one is going in this direction and the other goes in this direction, they will cancel each other out, and so on and so forth. This twisting, how much you twist depends on length, right? So it varies how much you're going to twist them by length. This is a very important thing that you should know. So let's talk about UTP first. So UTP has a three main components. one, it has an outer jacket, and then it has four wires. Let me draw them real quick. So we're gonna have blue, we're gonna have green, we will have wait, that is orange, and finally we will have brown. So we have three main parts when it comes to UTP, which is an outer jacket. So outer jacket is there to protect these wires from any environmental factors. Then we have these plastic lining for insulation, because plastic is a really good insulator. It doesn't allow, it doesn't conduct anything. Hence, it will hold in the current a lot more better. And finally, inside all of these wires, you have your copper wires. So there will be 8, because each of these is a pair, so you'll have 8. Now, why these 4 colors? You may ask, why blue, green, orange, and brown? Why is there no red? Why is there no yellow? Because in literally every single movie that we see, almost every single circuitry has red and green and yellow, right? But actually, this color is standard color that is actually designated by the TIA or EIA. I believe this is Telecom International Association. I don't know, but this is who determines the colors of these things. It's a standard. Now, why do you need a standard? Why can't any one of us like pick different colors? We can have all for different colors. Like I said, in most movies, there's a green, there's a red, and there's a yellow, along with maybe a blue. Well, if everyone had their own colors and if everyone had their own thing, who knows what part does what, right? So since we want everyone to follow a same set of standards and everyone to recognize the components inside, that is why there is a standard set by the TIA EIA for the UTP, right? So an unshielded twisted pair has 3 parts: outer jacket, plastic lining, and the copper wires inside. The STP is literally the same thing. So let me copy my majestic drawing. Right. So everything else stays the same except one part. What is the part, you ask? Well, I'm gonna draw this with yellow. The outer jacket changes. So the yellow part is now the outer jacket, right? The yellow part is now the outer jacket, and the white part is now actually an added part called the metallic shielding, right? So the only difference between both of these is a shielded twisted pair has a metallic shielding to fight against, or to be a little bit more preventative against electromagnetic interference. Now, we talk about interference, we're talking about something noise. What is this? Well, when it comes to uh, when it comes to cables and transmission media, there's something known as interference, right? So interference is, as the name suggests, any sources or something that interfere with the signal. So in this case, if anything interferes with the electromagnetic signal, sorry, if anything interferes with the electric signal that goes through these cables, it makes interference. So interference has uh, many types. Actually, there's 4 for now. There's noise, there's white noise, actually, my bad. That is also known as thermal interference, which is caused by heat. That is something known as intermodulation, that is caused by mixing of frequencies. There is something called impulse, which happens due to environmental effects like lightning. And finally, we have something known as electromagnetic interference, right? Which can be caused by motors and microwaves. So these are interferences. So how do you explain interferences or noise, right? It's also called noise. How do you explain it? Well, my answer is it is an external source of external source that tampers with original signal, causing it to lose and false data, making the final uh, interpretation of data impossible, right? So this is my answer that I have memorized. I would love for you, for every single one of you, to bring up, to have your own idea of what it is. So essentially, what noise is simply, now when we take electrical signals, we're talking about electrons, right? So anything that interferes with these electrons is considered noise. Now, for instance, heat can do something to electrons that's going to make it wonky. Intermodulation, frequencies mixing up each other, lightning, electron. So EMI will, or electromagnetic interference, can make electron go wonky. Hence, it will make the final interpretation impossible or hard, right? So that is what is called as noise. So we have learned interference right now. So let's go back. We forgot one, well, we didn't forget, we're right on time to talk about coaxial cable. What's the difference between coaxial cable and UTP STP? Well, coaxial has another added part. So it also has those four wires. It also has the same four wires that has. It also has, it has actually two different parts. So let's actually quickly erase the outer jacket bit. Let me also remove this for simplicity's sake. Go back to 4 pixels. Okay. So now you will have the outer jacket, right? But you will also have another added thing in between the jacket and the, I would like to say, thing. Okay, wait. No. So this can be considered as that. The added thing is every single one of these wires will have an external added jacket, right? So what are these parts? Well, we always have an outer jacket, but this is known as a woven braid, right? Woven braided sheet. right? And finally, we have a foil shield for each twisted pair. Where do we use coaxial? Well, coaxial is used for cable TV mainly, and hence it is very susceptible to impulses, meaning lightning strikes and so on and so forth. So, what are the connectors used by UTP, STP, and coaxial? Well, UTP and STP both use RJ45 connector ports, right? Whereas the coaxial uses B and C, right? So, this is very important for you to know what type of port that they connect. So that is, I believe, all about copper related. There's another guided media that we haven't talked about yet. Actually, that is the best of them all. He is the best among us. And that is the fiber optic cable. So, how does optical communication work? I mean, computers can't emit light. I mean, I think it's obvious what fiber optic cable does. Its signals are light signals, right? So a computer cannot emit light, nor can it decipher light, right? So how does it happen? How does it emit light and decipher light? Well, it has a specific device. The transmitter has a specific device that can emit light, and the receiver probably has a part or component that can decipher light, and the same thing can happen from either way, right? So essentially, the fiber optic cable is something of a wave guide, right? It's a wave guide that guides the light wave. Okay, so why do we use fiber optic cable? What are the benefits of fiber optic cable? Well, here are some very important benefits. Benefit number one is it is completely immune to electromagnetic interference. It's completely immune. Now, I had a question that if light is an electromagnetic signal, how can it be immune to electromagnetic interference, right? But, and the answer to that is very interesting because copper, let's imagine this is a copper wire. Copper wire has electrical signals. Electrical signals causes an electromagnetic field along it, right? So other electromagnetic fields can affect it. But light is simply an electromagnetic wave. So other electromagnetic interferences cannot affect it. So that's a little bit of a more you know, the more you know stuff. So back to benefits of fiber optic. So it's completely immune to EMI. It is best used for long haul communication or long distance communication. It has a higher bandwidth or speed, and it will most of the time deliver data with high quality. Very important things. These two are very important for good data transmission. So fiber optic cable mainly has two types: single mode and multi-mode, right? So let's talk about both of these. Single mode has a small core, whereas multi-mode has a large core, right? So you might say, multi-mode is better than single mode. Well, that depends because single mode is used for longer distances and multi-mode is used for shorter distances. Why is that? How? You may say, hey my god, larger core means larger. It should be better than this, right? Well, sometimes bigger is not always better. I wish he said that. Anyways, so how does fiber optic work? Well, it works on the principle of reflection or refraction. Essentially, there's a tube in the middle, right? And then there is a bigger tube known as cladding on top. The density of this will be greater than this material. So if anyone who studied physics knows, light will bounce off of this by using law of reflection. Now, what you're seeing here, what I've drawn here is we are using multiple signals to be transferred through this, right? This is actually multimode, where it has a bigger core and it uses multiple signals. So that's a very important distinction to make. Multimode has multiple signals. What about single mode? As the name suggests, it uses only one signal, right? So why is single mode having a singular signal and having longer distance, whereas multi-mode has multiple signals and shorter distance? Well, as you can see, once you have so many signals like this, if you stretch it out for too long, you can lose some part of it, right? Hence why we use single mode for longer distances and multi-mode for shorter distances. In actuality, we will learn about this a bit later, but multi-mode has a loss of 2.5 to 3.5 decibels per 850. Oh, sorry. So it has a 2.5 to 3.5 decibel loss per 1000 meter or per kilometer, whereas single mode has a loss of 0.2 to 0.3 decibels. Like, look at that. That is so low per 1000 meters, right? So that's a very big benefit of using single mode over multi-mode, right? So how does single mode achieve that? Well, single mode uses lasers, whereas multi-mode uses LEDs, right? And one more important distinction is single mode is very expensive, obviously, as you can see, and LEDs are, well, it's less expensive. Okay, so how does this work? What is this made of? Well, usually the core is made up of glass strands or silicone, right? Because it's a, as you all know, glass is very reflective. You see your beautiful face every day when you wake up, when you go to the bathroom, when you brush your teeth or do some other stuff, and that is a very good light reflector, hence why we use that for its core. And silicon is kind of similar to glass because it is also a really good light conductor. Think of it like that, right? So now we have a few connectors to talk about. Now, bear in mind, it's a bit hard to remember, but remember this. So there's something called ST, which stands for straight tip. There's something called SC, which stands for subscriber connector. Which reminds me, you should subscribe and leave a like to this channel. Frankly, I don't care. But if this helps you, a sub would be nice. A like would be better because that would show the algorithm that it helps people. Blah blah blah, that stuff. Anyways, next we have LC, which means lucent connector. And lucent connector has two modes: single mode and multi mode. Oh, by the way, subscriber connector is the one that most of our fiber optic Wi-Fi's use. So in Sri Lanka we have SLT fiber, and subscriber connector is what they use. Anyways, so LC, there's single mode and multi mode, right? Right. So how do you connect So there are four kinds of like connectors or something called as patch cords, right? So what are patch cords used for? Well, patch cords used for devices with various types of connectors. So single mode uses yellow and multi-mode uses orange or aqua. Okay, so what kinds of patch cords are there? Well, S there's SC to SC multi-mode, subscriber connector to subscriber connector multi-mode. There is LC to LC, losing connector that is in single mode. Then we have ST to LC, straight tip to loosen connector that is in multi-mode. And finally we have ST to SC that is in single mode. So all it does is connects two different devices with subscriber connector. This one connects two different devices with a loosen connector. This connects two different devices with two different connectors. One is straight tip and loosen mode, loosened connector, and the other one is straight tip and subscriber connector. Right? Perfect. I hope you understood this because we are not done. We are not even done. So where do we use fiber optic? So fiber optic is used in a lot of places. One, enterprise networks. It's also used in home networks nowadays because obviously everyone loves very fast Wi-Fi. Even I have this and I haven't paid for about 4 months now, and they are still calling me once every month saying, please pay your bill. uh, I should probably pay it. And next we have long haul networks that spans over countries. And finally we have it over submarine cable, where submarines, uses submarine cables, uses kind of very fast networks. They need, obviously, submarines obviously need it. So now we have learned about all of this, right? We learned about interferences. So there is something that we should learn along with all of this, which is called transmission impairments. Now, we learned about noise, right? So, essentially, what is noise? Noise has four types. There's white noise, there's intermodulation, there's impulse, and there's EMI, electromagnetic interference from other devices. So, there is noise, yes, but there's another very, very important one known as attenuation. And finally, there's something called crosstalk. Attenuation is simply loss of signal strength the farther from the source. So attenuation is loss of signal strength the farther from the source of the signal. That is what attenuation is. Crosstalk is something like this. Let's say there are two wires, right? So what can happen is the data from this wire can be transferred over to the other wire, creating something of a crosstalk. So this is an answer which we have to kind of memorize of sorts. Coupling of signals from one pair of conductors to another. That is what crosstalk is. So we talked about transmission impairments. We talked about guided media, right? So I believe we have finished all about guided media. And here is an overview of all what we have learned right now. So let us move on to unguided media. So, what is unguided media? Well, unguided media is something like Wi-Fi, Bluetooth. Its medium is usually air. So, unguided media has a lot of uh, cons. Like it has a lot of limitations per se. The first limitation is it has a coverage area that is less. Uh, it has very high interference. It's very susceptible to interference. There is a security risk in most places where unless it is if most devices or most Wi-Fi are heavily guarded, there is always a security risk. And last but not least, we have something of an issue which is it is usually a shared medium. What does it mean if it's a shared medium? Well, it has two main issues when it comes under shared medium. One, it is half duplex, meaning it either transmits or receives. So it either transmits data or it receives data. It doesn't do both at the same time. Who does both transmit data and receive it at the same time? That is full duplex. Now you might wonder, wait a minute, Yazim, my Wi-Fi doesn't wait till I upload something and finish to download something. It does both at the same time. How does that happen? That's because it does both of these like switching very fast, like almost instantaneous, right? Because of that, it seems simultaneous, but it is not. It just happens so fast. It's like flash phasing from here and here that it looks like there are two flashes, right? So modern Wi-Fi systems have something called, sub channels where it chops a main channel into smaller sub channels. And what will happen is this is the closest we are gonna get to full duplex mode on Wi-Fi's, right? So this is something that you should know to understand why it is half duplex and the issues related half duplex. The second issue when it comes to shared medium is the more users there are, the more users, the less bandwidth per user. So, and as I said before, we cannot predict how many users are going to be there to a specific Wi-Fi, right? We cannot predict specifically. So it has to adapt to, different numbers of users. So it can sometimes have a high number of users, sometimes it can have a low number of users, right? And remember, we learned about half duplex. It's also half duplex because it uses something called a four frame exchange where it has to wait for acknowledgements using DIFS. I highly recommend you go check it out. So so this is what unguided media is. It has all these limitations, right? But what about its pros? Well, it has no cables or very less, right? Very less cables. So you don't have to be walking around connecting your phone to the Wi-Fi. You can simply connect your phone to the Wi-Fi. It's most of the time it's easy to install and it can be used anywhere at any place, right? So these are the pros and cons of unguided media. But let's talk about interference for uh, guided media. So we talked about attenuation for guided media, right? So attenuation is loss of signal strength. So let's say you have copper, which uses electrical signals. You can lose the power, yeah, exactly, the power of the signal as time goes by. When there's light signals, there's the amplitude. So there's the amplitude. So the amplitude may decrease and you can lose probably power. Essentially, this loss of signal, right? So how do you lose for unguided media? How do you lose signal strength? Well, it happens, use something known as inverse square law, or I believe it's free space. Let me check, give me a minute. Oh yeah, it's the free space something something, I'm not sure. What it essentially means is, let's say we have a source over here, and I'm going to go 1 meter over here, and I'm going to have a place called A. I'm going to go another meter over here, and I'm going to have a place called B, and so on and so forth to the to power n, right? So there's going to be n meters here. So the signal strength, if the signal strength is x at the source, at n, position n, the signal strength will be x over n squared. So it will lose its signal strength exponentially. Now, as you all know, we will talk about it in a file. We will talk about how attenuation happens for guided media. It is usually per 100 meter, it's per 1000 meter, whereas this is not per, it's like it is per meter, but it becomes exponential. See, this is a linear loss, whereas this is an exponential loss, right? So it's very important to remember that attenuation in unguided media is way bigger than in guided media. Second off, we have something known as penetration loss. So let's say a signal will either go through a medium or reflect off of a medium, either one of those two. What will happen is it will lose some of its signal strength. So we have a few values here and there. So it's best to remember. So if there is a bookshelf, it loses about 3 decibels. Oh no, a bookshelf, it loses 2 decibels, and it loses 2, and it retains 2/3 of its original strength, right? Then we have concrete, where it loses about 12 decibels, and it retains only of 1 out of 16th of its original strength. Then we have glass, where it also loses about 2 decibels and retains, I believe, oh no, this glass is 3 and it retains half of its original signal strength. Uh, then there is brick, where it loses 10 decibels and retains 1/10 of its signal strength. Uh, then we have elevator shaft, I'm just gonna call it shaft, where it loses about 30 decibels and retains 1 out of 1000th of its power. Uh, and finally, we need one more. Let's go 2 more actually. So marble, it loses 6 decibel and retains 1. I'm not sure how much it retains, but a door, a solid wooden door, also uses 6 decibels, and the signal retains 1/4 of its signal strength, initial signal strength. So this is what penetration loss is. And finally, let's now talk about the stats. So let's talk about attenuation stats, right? So attenuation is highest in UTP, and it decreases for STP. It decreases a bit more for coaxial, then it goes for multi-mode, then it goes for single mode, and finally we have wireless, right? So UTP has an attenuation of 1 decibel to 2 decibel per 100 meter, right? At 100 megahertz. So if the signal's frequency is 100 megahertz, right, per 100 meter it loses 1 to 2 decibels. STP loses about 0.5 decibels to 1.5 decibel per 100 meter at 100 megahertz. Coaxial loses 0.2 decibels to 0.6 decibels also per 100 meter at 100 megahertz. Now, megahertz is the frequency that we use because it's an electrical signal, right? Whereas multimode and single mode is optical cables that uses light signals. Keep this in mind. So multimode is 2.5, loses 2.5 decibels to 3.5 decibels per 1000 meter at 850 nanometer, right? Whereas single mode, as we talked about, loses only 0.2 decibels to 0.5 decibels per 1000 meter at 1550 nanometer. Wireless, I'm not so sure about it, but as you can see here we have amplitude. Light signals depend on amplitude, right? Hence why we have, if it's a set amplitude, it loses this many decibels. That's what is this attenuation graph, right? So that is all about uh, unguided media. So this is a quick summary of what we have learned about attenuation. So I think it's best that we don't waste any time and move on to link layer. Interesting, isn't it? So let us finally talk about the link layer. Now here's a very important distinction you need to make. It's a mistake that I made during lecture. Encapsulation begins at transport layer, right? Not the application layer. And it ends at link layer, right? The physical layer, all it does is convert this into bits and transmit it over a transmission medium via signals. Let it be electric or electromagnetic, right? So I made this mistake. I hope you guys will not. So let's move on. So before the link layer, it's also called data link layer. Before that, we have the network layer, and afterwards we have the physical layer. Now, the network layer sends datagrams, whereas the link layer has frames, which will be converted in the physical layer to bits. So today, and in this part, we're going to talk about the use of link layer or its purpose in life. And then we will talk about MAC address versus IP address. Then we're going to learn about link layer protocols. And then we're going to learn about MAC addressing. So let's begin by talking about what is the use of the link layer. Well, it obviously encapsulates datagrams into frames and then it does is it includes the MAC address of the device, and then it is used for detecting collisions, and it does something known as an error checking, right? So before I believe you guys understand what encapsulating datagram into frames means. So let's talk about including MAC address. Why should it include MAC address? What is the use of MAC address? And what are the common misconceptions about MAC address and IP address? Well, here's a very important. MAC address is unchangeable, right? It is assigned at birth or something like that. Whereas IP is assigned by the network. So MAC address is always used between local devices, whereas IP addresses is used between not only local but the entire network. So global network and such, so forth, so forth. So the best way to think about this is IP address is the town and local address is the house address, the specific house address. So IP address can be used to go from above the router. Let's say we have Wi-Fi router that we are connected to. So it goes above this router and it goes into the internet connection or a server, so forth and whatnot. And it comes back, and from the router it connects to your phone using your phone's MAC address. Okay, so that is why it needs include the MAC address, right? Because it needs to find your phone in your network. In your case, in your LAN, you are connected to Wi-Fi, it has to find your phone. Now I believe you remember that we learned that from one end host to another end host, it goes through all 5 layers, right? 5 all the way towards one application, all the way towards physical. But we have routers that go 1, 2, and 3. And we have access points that goes from 1 to 2, right? So, and also switches have go up to 2, right? So what does this mean? Well, an end host goes all the way up, goes encapsulates and then decapsulates all the way towards the network layer. Here what happens is it removes the MAC address and it changes it to the specific device that it should go to. Again, it goes towards the switch, it removes the MAC address and changes it, so on and so forth until it finally does. What you must know is MAC addresses for each device does not change, but MAC addresses will change on the packet, per packet, like per device, per hop. IP address is assigned by the network, it is flexible, but it will stay the same throughout the packet. This is a very important thing that you should know. Okay, next we have to talk about detecting collisions. Before we talk about detecting collisions, we should know that there are 2 types of main unguided media. Ethernet, which is guided, and we have virtual LAN or Wi-Fi is the one. So the IEEE are the people who set standards for these kind of stuff. And there's an IEEE standard for Ethernet, which is 802.3, and Wi-Fi has 802.11 that has A, N, AC, and AX, right? So they set these standards for Ethernet and Wi-Fi's, right? So what is these standards for? Well, Well, along with these standards, there's something else known as collision detection, which is CSMA collision detection, CD, and CSMA CA, right? So what is this? So what does CSMA mean? CSMA is carrier sense multiple access. Carrier sense multiple access. CD is collision detection, whereas CA is collision avoidance, right? So collision avoidance is also one of the reasons why Wi-Fi uses half duplex mode, right? Because it avoids, it's vice versa. Okay. So collision avoidance is because it, since it cannot like detect how many devices are there or predict how many devices there at a certain point, it has to adapt. So one of the adaptations that it does is it avoids collisions rather than trying to detect collision. Whereas in Ethernet, they know how many devices are connected, they know the issues that can arise, so it detects collisions and steers clear away from them, right? So that is all about detecting collisions. Now, finally, we have the most interesting one known as error checking. So, how does error checking work? Well, I have learned something known as an error checksum, but AI says it's known as a CRC, which is cyclic redundancy check. So, I don't know which is which. I would highly recommend you go look this for yourself. Remember, self learning is one of the best ways to learn. So, let's take an end host transmitter and let's take another end host, a receiver. We are only caring about link layer 2, a data link layer, the second one, and the physical layer. Even you don't even need the physical layer. So what the link layer does is it checks the payload from above and it creates an error checksum value. Let's call it I'm sorry, let's call it 4. What it does is it checks the value, it attaches this value onto the payload, and it sends it over. So what the enforce does is it will again do its own error checksum. It's not this checksum, it does its own error checksum. It's going to check if it's equal to 4. And if it is, it will send it up. If not, it will drop the packet. So here's what will happen. Since you know it is 4 and x, if x is equal to 4, it passes and it will be sent upwards in the layer, upward layer to decapsulate and all that. If x is not equal to 4, the packet is dropped and retransmission is requested. So retransmission, packet dropping and retransmission usually happens on Wi-Fi, not the Ethernet. Usually it never happens. It usually happens mainly on Wi-Fi. So this is one of the many error checking that it does. So usually it's a polynomial based check value, this value, so we don't have to get in the maths into it too much. And finally, we will learn today, the final topic is addressing, specifically MAC addressing. So it has 6 bytes or 48 bits, right? And we use the hex code for this. So here is the 6 values, 6 bytes, 48 bits. It can range from 0 to F, and what will happen is every single device has its own specific uh, 9C, that's not E, that's C. Think of it like numbering. Okay, so I'm just going randomly off my head. This I have no idea whose MAC address is here. I sincerely hope I'm not stealing someone's MAC address. And last but not least, let's have a lucky number 69. Right, so this is uh, what is maybe known as the, maybe it can be the source MAC address, but there's also destination MAC address where we know the next where we put the next device's MAC address. So there is a very interesting one here known as the broadcasting MAC address. But before that, let's think about something. Let's say there's devices A, B, C, and D. If A needs to send to B, the source will be A MAC address and destination will be B MAC address. If D needs to send to A, the source will be D and destination will be A. But what if A wants to send to everyone? Well, then the source address will be A, but destination address can't be B plus C plus D, right? Hence, what is called the broadcasting address, which is FF, 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 FF. Now, a very important note, all of them must be either what lowercase or uppercase. We can't have two different things. Then we'll have like, I don't know, a lot more than hex, right? So this is what's known as the broadcasting address. If the destination address is set as this, every device will get the message, the address or something like that. So that is all we have learned these past 2 weeks. I hope you understood. I hope you have learned something. I hope this was of use to you in some way. Anyways, thank you for coming. And I want you to remember one very important thing. Remember, you are loved. Remember, you are cared for. Remember, you are important. If you have any help, if you need any help, please feel free to reach out to someone who you care about. I know studying is hard. I know studying can be sometimes stressful. I know sometimes you feel that you are inadequate, but remember, you are not. You just need to work a little bit more harder, and anything is possible if you put your goal to it, if you put the time to it, right? So keep that in mind. Don't do anything brash. Don't do anything drastic. Don't take a permanent solution for a temporary problem. Okay. Remember, you are loved. Remember, you are cared. I have my mid exams tomorrow, and in coming week I have my mid exams. I hope the ones who have their mid exams tomorrow or the days after, or whenever you're watching this, if you're watching this before an exam, I hope you do really good on that exam. And that's all. Have a great day.